Good morning. So this is a continuation of lecture 1. So in the lecture 1 we have introduced what is a multivariate time series, and we have seen what are its mean, variance, covariance matrix, correlation matrix, as well as cross correlation matrix. That is something new to the multivariate time series, because you can have correlation between one component and the lags of the other component. So that leads to what is known as cross correlations. So we have defined that, and then we have seen how these computations can be done. So in today's lecture, we are going to continue with that, and here we will be introducing how those quantities can be estimated directly from a given multivariate data without getting into a modeling framework. Okay, so modeling framework will be in lecture 3. So here, before starting, I would like to introduce a couple of notations. For example, here let A be a matrix, M by N matrix, and each of those, the column, I call this as vector A1, vector A2, etc., vector AN. So there are N columns and M rows. So that's what M by N matrix. So the vec A, that means the vectorization of this matrix. So basically what we are doing is vec A is nothing but you stack all these vectors one below the other. So it's like A1 below that, A2 below A3 below A4, etc. And so in the notation wise it can be written as A1 dash, A2 dash, etc., AN dash, the whole transpose. So that gives me a Mn by 1 vector. Okay, Mn by 1 vector. So every element you simply uh, stack them. Okay, so that is called vec notation. Then another notation which we would like to learn is what is known as Kronecker product. So suppose A and B are M by N and R by S matrix respectively. So A Kronecker product B is nothing but each of the element of A is multiplied by this matrix B, all the elements of the matrix B, and then you just place that there. So it is like A11B, A12B, etc., A1 and B, A21B, A22B, A2NB, etc., AM and B, AM2B, etc., AM and B. So this will have M into R rows and N into S columns, or MR by NS matrix. So this is called Kronecker product. So basically element of each of the matrix of this first one is multiplied by this. So order is not a problem at all here, whatever the order, because this could be different. So what you are going to get is MR by NS matrix. So we wanted to have, or we want to have these two operations to be learned. Of course, there are quite a number of operations. You can see the properties of this on behind in the appendix of your textbook by, say, multivariate analysis. If you are interested in learning more on this, how the inverse work, how the transpose work, etc., etc. We are not getting into that for the time being. So let's start defining the estimators. So suppose we have a sample xt. Now this xt means I have k by 1, each of them is a xt for t equal to 1 to n is a k by 1 vector, each of them for t equal to 1 to n. So this form a multivariate times. So this is like you have the multivariate observations that you have. You have learned the multivariate analysis, so where you have dimension of the vector is p, and then you have n observations. So I am talking something similar. I have n observations. It's not observation, it's a time series, so it's like sequential. So we have this, and then each of them is of dimension k. Now the sample mean vector and the sample covariance matrix is defined like this. The sample covariance matrix can be defined as, oh, I have to put a hat here. I'm sorry. So this is with a hat, these two hat. So the sample mean vector is this, and sample covariance matrix is this. And the lag H, sample cross covariance matrix. Sample covariance matrix is this, in the sense that we have learned the definition. Now I am suggesting you an estimator. So this is these two I'll replace it with at here. So that's an estimator. From the given data, we are estimating them. So this is what the gamma 0 hat, and this is what the gamma h hat. What is this gamma h hat? It is lag h. That means the covariance between xt and xt minus h. Okay, that is what this is. So I have this particular definition for that. And the corresponding correlation matrix is, of course, we have seen this definition, D inverse gamma H, gamma hat H, D hat inverse, where this D hat is diagonal of this. So we have this R, what is this? These are basically the square root of the variances, basically. This is 1 means is the variance. KK is the variance. That means variance of each of these components. And you construct a diagonal matrix. And then if you take the square root of that, then it's a standard deviation. So these are basically the standard deviations of the components of this. So K components are there. So the ith element of gamma hat 0. So these corrections I will make. I have to put a hat here. I have to put a hat here. Now, if xt is stationary, a linear process following a multivariate normal distribution. Now, in this discussion, I haven't really assumed that this is normal. It could be just a multivariate any distribution. So, if I assume that this is a multivariate normal, then we are not proving that, but it is possible to prove that this is a consistent estimator of this. What is this R? R is nothing but the correlation, cross correlation matrix, which you have seen in the lecture 1. So here, this is a consistent estimator if you have a normality. Now, you can also claim the consistency and its asymptotic distribution theory with higher moments assumptions. Like, for example, if you can assume the fourth moment exists for xt, then we can still prove the consistency of these estimators. Which estimators I am talking about? I am talking about the estimator of the mean vector and the covariance matrix, as well as the correlation, the estimator of the correlation, cross correlation matrix, CCM, cross correlation matrix. Now, what happens that in the case of univariate, we have seen that we get the autocorrelation function help us to basically to study the strength of the correlations as lag changes. So now here, because there are several components, how this can be done? Well, one way is that you can again go for the cross correlation plot for various lags. So I'll just consider the cross correlation plot for lag 1, lag 2, lag 3, etc. So which can be computed. The command CCM of MTS package of MTS means multivariate time series package of R can obtain the cross correlation plot. But what happened that to get a, in the univariate case, you get autocorrelation, and then once you say the autocorrelation, you can see that there are two lines, which is basically, 2 upon square root of 1 upon square root of n, and then you see that whether you are within that range. So if you are within that range, you can see that these autocorrelations are not significant, otherwise we treat them as significant if it is outside that range. So something similar, a simplified matrix can be considered here. That simplified matrix is, it's like you get a matrix of plus, minus and dots. So plus stands for a significant one, minus stands for, it's like this is beyond the minus square root of n. So this is basically high negative correlation, and this is like a high positive correlation. So both are significant, and this means that the correlation is not significant. Now these are obtained not arbitrarily. One can, as I told you, with the appropriate assumption, it is possible to get an asymptotic distribution theory corresponding to this, which we are anyway avoiding, because for that we have to learn martingales and central limit theorem for dependent random variables, etc. But the logic is same. the components of this matrix, we can prove the asymptotic normality, or the matrix itself, we can prove the asymptotic normality. And this is a kind of confidence interval. So what we are doing is we are constructing a matrix where the entries are significantly positive, significantly negative, and somewhat insignificant. So that's what you're saying. So if I have more of this, it basically gives me some idea whether the cross correlations are significant or not. So that's what called simplified matrix as such is used to summarize the CCM. Now, in univariate time series, we have seen that we have the one of the tests that we use is Ljung box test. And what is this Ljung box test? The Ljung box is a particular case of the Portmanteau test. Portmanteau test is basically summing the sample autocorrelations and then norming it by appropriate functions of n. And then once you have an asymptotic theory, in fact it has a chi-square distribution theory, and then therefore we can use the chi-square table to see whether the particular lag of correlations are significant or not. The same thing can be done in the case of multivariate also, or the multivariate generalization of Ljung-Box test is available. Things are a little difficult in the multivariate case. For example, if I'm testing this hypothesis that M correlations, cross correlations are 0, against that at least one of them is not 0. So these are matrices. So the multivariate generalization of the Ljung box test is given by this statistics. So here this is n square and minus its trace of this quantity. So trace of this quantity, where this is already defined in the previous slides. In fact, I forgot to put a hat here. So this is defined, this is defined. So you have this is defined, and we can just simply compute the trace of this, and then it is proved that those proofs I am avoiding. It is proved that this has a chi-square with mk square degrees of freedom when these are all 0. This is 0 is essentially same as this is 0, because this is the covariance, and so the correlations can be tested. So of course in this is basically under the normality, this is even if you don't have the normality, many a time it is possible to people use this, and in most of the cases we actually have the normal distribution. So we sort of see, we basically consider multivariate time series with the Gaussian. I mean, like other things are pretty difficult to handle, because conditional distributions, marginal distributions, all these things are really difficult when you go away from the normality. So if you have a normality for xt, and if under the null hypothesis we can show that this is a chi-square with mk square degrees of freedom, so one can compute this and then see whether this is significant. If it is significant, we can say that correlations of lag m are significant. Now this, you can write this in a slightly different way using the vec notation, because here is a trace, so we can actually connect the trace and the vec, and then it is possible to change these covariances into the correlation, because you know that this is this into this inverse actually should gives me the correlation. So I should have the correlation matrix, and you can actually use this simplified format. This is called the simplified format. This is one and the same actually. Only thing is that here we are representing in terms of the correlation. Here I have represented in terms of the covariance. So under the null hypothesis, this both are same. So I'm using it by the same notation. Asymptotically chi-square distribution. Now you might have seen that in the univariate case, this, because there is some kind of a biasness for this, so there is a bias adjusted version of this, and that's called that was suggested by Lee and Mcleod, and that same Lee and Mcleod test can be generalized in the context of multivariate time series as well. So that is what Lee and Mcleod test, the same thing, plus this is the bias adjusted. So you adjust the bias like this. What is M? M is a number of lags that you are considering to compute this. So M is that M which we use in the univariate case as well. So this is called Lee-Mcleod test. This is same as what you can see, what you have written here. So this is exactly similar. Only thing is that we have added a bias correction term here. And the asymptotic distribution is same. Lee and Mcleod also have the same asymptotic distribution, mk square chi square. chi-square with mk square degrees of freedom. And yeah, so the command mq mx lag 10, I mean, oh sorry, this should be lag. mqx lag 10, this should be lag 10. 10, of course, you can replace it with any number. I've taken m equal to 10. This is compute the LB statistic in R. Okay, the MQ is the command for that. MQ actually, it's coming from here. Uh, M is the order, and I mean Q, that's the terminology used here. Okay, now there's an exercise for you. So here what you're supposed to learn how the series, multivariate time series look like. So what is supposed to be done here, you take A as this matrix, and you take ZT. ZT is a bivariate normal distribution with mean 0 and the variance covariance matrix this. So you generate observations from a bivariate normal with mean 0 and variance covariance matrix this. And of course, you can take x naught as z naught, I mean like as to a starting value. And then you develop on x1 as a x naught, x2 as a x naught plus z1, I mean like that. So we can get a series of xt. So I have asked you to generate 200 observations. Now observation here is a vector, is a 2 by 1 vector. So you will have 200 vectors, each of dimension 2. Okay. Now you need to plot the series. You can plot them separately. Plot the series. Compute the first 5 lags of sample CCM. So you get the sample correlation matrix. Use the R to get this. Get the sample CCM. CCM is cross correlation matrix, and you test this hypothesis. So this hypothesis can be tested using this statistics or this statistics. So command type already told you. So this is available. I mean like you can directly test it. So what are you trying to test? You're trying to test whether the correlations are 0 or not. The first 10 lags correlations are 0 or not. Against that, at least one of them is non-zero. So complete this, that will give a fair amount of idea. Now the enthusiastic people can continue this exercise. So this is a vector autoregression 1. You change the role as zt plus some a zt minus 1 equal to xt. So xt equal to zt plus some a x zt minus 1, and then generate similar kind of zt and get that xt series, and then do the same thing for that exercise also. So basically what are you generating? You are generating a vector moving average model of order 2, 200 observations from that, and then do all these exercise. Okay? Yeah, that's for the time being. Thank you.